Hi, this is Kumar Singh from Design Analytics LLC, and you're watching another episode of Throwback Thursdays. Well, let me actually list some areas, right, without any context to get started. So, computer vision is the broader area. Within that, we have image classification, object detection and localization, facial recognition and verification, scene understanding, just some examples. Then the other bucket is natural language processing, like text classification, document categorization, machine translation, speech and audio processing. You have healthcare and medical imaging, disease diagnosis, radiology, retinal imaging. Then the other bucket is autonomous systems like self-driving cars, drones and robotics. Biometrics and security, fingerprint recognition, surveillance systems. Industry and manufacturing is another bucket. Defect detection, smart agriculture, remote sensing, satellite imagery. Then art, media and entertainment, image generation, super resolution imaging, deep fake generation. Finance and retail, document recognition, customer behavior analysis. The list can be long, but what is this list about? Right? Why did I start with such an abstract thing? Right? Well, all these different applications leverage one single type of algorithm, convolutional neural networks, very widely used deep learning approach, right? And in this episode we are going to go through the history and try to understand how exactly CNN architecture came into existence, who proposed it, when it was proposed, right? So I highlighted in a post this morning on LinkedIn that the genesis of this CNN architecture was a paper that was published the year I was born, 1980. Right? And the concept or the architecture introduced in that paper was called neocognitron. Right? So this was the research paper that actually proposed the neocognitron approach that kind of was an inspiration for the modern CNN's convolutional neural networks. So what exactly did this paper propose, right? It proposed a multi-layered neural network model designed for visual pattern recognition, which, as per the author, at that time they thought it was robust to shifts in position of the input. Right? The network proposed, right, was self-organizing, which basically is unsupervised learning, right? So patterns are basically repeatedly shown to the input layer, and through internal adaptation, quote unquote learning without a teacher, the network builds up internal feature detectors. So as you see in this diagram, it starts with an input layer, photoreceptors array, followed by several modules, each composed of two layers, S cells, right, from simple or lower order hypercomplex cells, and C cells derived from complex or higher order hypercomplex cells, right? Then each module, S layer followed by C layer, is arranged in cell planes, many feature extracting units spread across positions. Within a plane, synaptic connections are similarly shaped, right, shifted in position across the input field. And as you go deeper in layers, receptive fields grow larger. So deeper cells can see more of the inputs, as you can imagine, right? This helps build invariance to small shifts, distortions or changes in size. So if you are familiar with convolutional neural networks, you can already see how this inspired modern day CNNs, right? So if we were to summarize some of the key aspects of this paper, like it introduced hierarchical feature extraction, right? So Fukushima, the author, he built a layered architecture where each stage extracted progressively more abstract features, right? And now you can see the similarity here, right? Another key feature could be, like aspect of the research could be the shift position invariance, right? The S cell and the C cell aspect. Self-organization, organizing learning, the unsupervised learning part where the model adapted feature detectors through repeated exposure, biological inspiration, right? Actually, Fukushima, I think he explicitly cited Hubble and Wiesel's work on the visual cortex, like simple and complex cells, right? And the neocognitron approach mirrored that biological hierarchy in a computational model. Right? So that was the beginning of the CNNs, the idea of the CNNs. So how did that study basically lead us there, right? This specific neuroscience connection and this paper influenced another scientist, Lee Kuhn, and others in the 1990s. So LeeNet 5, I think introduced by Lee Kuhn in 1998, has actually credited Fukushima's neocognitron as inspiration when he introduced convolutional plus pooling layers trained with backpropagation, where we came to very close to the current architecture of convolutional neural networks, right? So introduced CNNs as an effective architecture for image document recognition. He also showed that CNN outperforms other methods, right? So I think some of the comparisons was KNN, SVMs, PCA, fully connected MLPs, and the data set that he used to show that was MNIST data set. He proposed graph transformer networks. It was all proposed in this research paper, by the way. He proposed graph transformer networks to unify multi-module systems like segmentation, recognition, language models, all under one trainable framework with global backpropagation. This paper also provided practical validation through bank check reading systems, I think, so real world application that actually achieved state-of-the-art performance and were actually deployed commercially, reading millions of checks every day. So the framework here was basically built on three principles, like local receptive fields, like neurons look at small input patches, weight sharing, where same filter applied across positions, subsampling or pooling, which reduces the resolution, then increases the invariance. So there's this hierarchical structure, as you can see here: convolution, subsampling, fully connected RBF output layer, right? Some of the key traits was that it learned features directly from pixels instead of relying on handcrafted feature extractors, right? And training was done using stochastic gradient descent with backpropagation. And at this point, if you're familiar with CNN and if you followed some of the high-level overview of Fukushima's C cells, you can tell that the pooling mechanism in CNN is basically Fukushima's C cells modernized. The layered receptive fields idea, right, of the paper became the backbone of deep architectures, right? So if compared to neocognitron, while neocognitron lacked backdrop, like weights in S layers were updated by local rules, it demonstrated the viability of a multi-layer trainable translation invariant vision model, a radical idea at the time. So we can summarize that Fukushima's neocognitron actually provided the blueprint for CNNs, right? Hierarchical layers, local receptive fields, pooling for invariance, right? And then Lee Kuhn and others modernized it with backpropagation and supervised training, which transformed the neocognitron's theoretical promise into the practical power of CNNs that drive modern computer vision. Well, thanks a lot for watching. I will see you again next week.